Welcome back, everyone. I'd like to introduce Jeremy Rotstein. Jeremy is a systems engineer with a background in industrial control systems, dabbles in MicroPython, and had the displeasure of being my colleague for several years. Take it away, Jeremy.
No, it was fun. It was fun. G'day. Yeah, thanks for that, Chris. Whenever I go to PyCon, I've always thought it'd be nice to know, ahead of time when a talk's going to get to the really juicy Python content. So it's coming. I promise you, we've just got to get through some conceptual stuff first. So in one word, this talk's really about the notion of reliability. And giving attention to an aspect of app reliability that's often an afterthought or sometimes even overlooked entirely. And by then it's too late. So when people say, this app's rock solid, yep. This app's rock solid, it runs like a dream, what they're really saying is that it handles all the edge cases well, it's engineered to be fault tolerant, has good performance, it does what it needs to do well. What they're talking about is robustness. The app is robust. And it's robustness that what we tend to think about and what we put all our energy into achieving. All those coding standards, code reviews, design meetings, refactoring sessions, testing, all that, it's all designed to achieve robustness. But as you know, if there's something we all know, it's that despite our best efforts, our applications can fail. And if they can fail, they will fail at some point and in totally unexpected ways. So shouldn't we be prepared for that in some way? So when it does enter that failed state in production, isn't reliability more of a time measure about how long it takes to get the system working again? So it's the repairability of your application now that becomes the crucial factor. It's not just how robust your app is. That ship has sailed and I guess sank. So if you're a developer and a maintainer, so you've got skin in the game, you're developing and you're maintaining your own product.
Sorry.
Beard?
Can I just adjust the mic a little bit?
Yep.
Sorry, it's just scraping just a tiny bit.
Better to get it right. Yep, cool. So yeah, if you're a developer and maintainer, you've got skin in the game, you're maintaining what you've developed. It comes down to doing all the right software craftsmanship things to extend out that time between production bugs. So that's the developer side. But on the maintenance side, you also need to knuckle down and have some tools and techniques to keep the time taken to fix these production bugs as short as possible. And let's not forget what the real goal is here. It's all about us being able to sleep well at night and not get woken up. So I'm sure most of you have seen this type of chart before. It's normally used as a lesson to try and catch bugs as early as possible in the process, because the later and later it gets, the more expensive it is to fix. Not just in engineering time of you, but in costs to the end customer from the downtime and the defects of their products or services. So if you improve repairability, what you're really doing is driving down the cost at the last stage where a bug is most costly. There's other advantages for the other stages too, but the main one where repairability has the biggest impact is at that last stage there. And if you break down what goes into fixing a production bug, you've first got to find the cause. So you're in what I call a plumber situation. A plumber can't fix a leak, let alone even estimate how long it's going to take unless they know exactly where the leak is. So then you've got to apply the fix, both in terms of changing your code and deploying it. And it's that first part, the time to find the cause, that can be the really, really hard part, and that's where having diagnostics helps the most. So when we're talking about diagnostics, its definition is kind of contained within the word itself. It's a tool for diagnosing. It's a tool to help you know the diagnosis. It's for knowing the cause of the problem. Or even finding out whether there is a problem or not with your code, which is still really useful because so much of troubleshooting complicated systems with many moving parts is about eliminating those potential root causes, you know, Sherlock Holmes style, until you arrive at the truth, however improbable it is. And how many times does it come up, whether, you know, you or someone upstream says, oh, it's working for me, sorry, can't replicate the problem. What they really mean is they can't find the cause of the problem. And if they can't find the cause of the problem, then you're out of luck thinking they can even fix the problem. Sucks to be you. Now, to me, this indicates a failure. Yep. Yeah, it's all good. Yeah, right. I'm doing this tomorrow, by the way. I'm doing his job tomorrow. Yeah, so to me, that type of situation indicates a failure to have enough good diagnostic tools at hand to find the root cause when you're inspecting the so-called crime scene of a failed application. Tuck it in somewhere.
Yeah.
All right, let's go. Yeah, so you don't have the right diagnostic tools. It's not so much to do with having perfect replicas of the real-world installation setups lying around on your desk to probe. In practice, it's really hard to do that. There's just so many possibilities on site, and although obviously that would help a lot too as well. So without much data or tools, in that situation, you're forced to resort to the software equivalent of physicist Richard Feynman's famous problem-solving algorithm, at least according to his colleagues. Just think really hard and then come up with a solution. That's not a situation you want to be in when time's of the essence. I'm told also in Oppenheimer he's basically relegated to a bongo drum player. So I'm not too happy with that, Mr. Nolan. So let's look at some of the attributes of software-based diagnostic tools before diving into some concrete examples. So firstly, it's got to be on demand. So that is, we don't normally require the tool. It's not part of the core intended function of the application. Everything works fine without it. It's only glanced at when needed, and ideally the data is only generated and displayed when it's needed as well, making it really light on resources. So being light on resources, including cost, is really important, especially on constrained, Internet of Things, IoT devices, where there's thousands in the field, and they're charging per device. It's permanently attached, or probably better stated, embedded. So what I mean by that is it's part of your application. The diagnostic tool is part of your application, available for use at any time. It's not some separate tool that you need to connect or spin up when the time comes. And it's also part of your code too, like tests, except, yeah, this tool's designed to be run in production when you need it most. And you don't really want it to be a separate tool, because it's going to be just another tool in another repo you've got to maintain and potentially keep in sync with your app. And if you have to stop the application, attach the diagnostic tool, then restart the application, you're not preserving that crime scene, so to speak. There's huge value in seeing inside a partially failed but running application. I really hate that I've used this term, but what we're talking about here is diagnostics being human-readable. It means you can't just provide a JSON dump of your app state accessible via some API and call it a day. You can't just debug log everything at high resolution and spew out pages and pages and logs and call it a day. It's more about being information rich, having a high signal to noise ratio, if you want to call it that. And I guess it implies that the diagnostics you create are highly customised for your application to spit out exactly what you need to find to find where the issue is and not much else. Otherwise, it's just going to take too long when you need it to track down the cause. And finally, this one's about being able to see inside your application while it's running. So all the necessary nuts and bolts, the so-called system state, the app state. It's all in service to answer that basic question. Is it working? And if not, where has it failed? So this is that preserving of the crime scene aspect I talked about. And this attribute really determines whether the diagnostic tool is useful at a more fundamental level. So let's look at some real-world examples of diagnostics. Here's your classic car dashboard. It's pretty good, I'd say. When your car acts up, it tells you where to go and look. It's information rich, lots of symbols and icons packed into a small area. I just subtract points here for being on demand because you do kind of need to know the speed you're travelling to drive legally, and you've got to know whether you've got enough petrol. So it's still part of the core functionality of the car. Here's a so-called bed of nails setup for testing voltages and signals at various points on a printed circuit board. You can see the pogo pins underneath, probing the circuit traces of that upper board. And I subtract points there because it's not embedded. You've got to attach it. And unless it comes with a really intuitive UI, all it's doing is spitting out raw data that would be hard to comprehend. This is GitHub's operational status page. Pretty good, I reckon. You can clearly see where the issue lies if you're a customer. It condenses a lot of services behind those little green dots, which is also a little bit of a shortcoming, I reckon. And the incident history button is really useful for tracking down something you're waiting for resolution on. Now let's look at your typical logging, high-res logging. It's certainly on demand and permanently attached, but it's normally quite costly in terms of the time to trawl through the pages to trace an issue. And if you're only logging errors, so low-res logging, it's often too terse to really know how your app's functioning at any point in time. And you might not get that full breadcrumbs, as Sentry calls it, to track down all the steps that led up to that unhandled exception. Which leads us to our standard Python debugger. Again, not permanently attached and way harder to use than logging, otherwise everyone would use it all the time. But does a really good job on telling you the internal state of affairs. So if this was somehow running all the time in our app with minimal overhead and customized just for the information we need presented in a really easy to digest way, I reckon that would be amazing. So let's keep that in mind. Now for Internet of Things, industrial control, even our connected universe, that's where diagnostics really shines, because you don't have that comfortable environment of the cloud. So your app could be in a factory controlling an important piece of equipment on the line, could be on a farm in the middle of nowhere collating sensor data and using it to control machinery at irrigation time. It could be in someone's house, and they certainly did not consent to sending you logs, and rightly so, given all the privacy issues that come with that. And yeah, it also could be located in a highly secure, inaccessible private network, self-hosted by the customer for security reasons. So in all those examples, it's quite likely either you've got no direct comms or you've got very, very limited comms, if that. your standard high-res, heavyweight and costly cloud-based logging setup is just not an option in a lot of cases. So unlike in the cloud, your application in those sorts of scenarios can't just be designed to exit on unhandled error and rely on your horizontal scaling behind a load balancer to pick up the workload of the faulty unit. There's no horizontal scaling. There's no Kubernetes, there's no failover to a disaster recovery site, there's only one unit. And in this situation, you're often, like it or not, you're relying on the customer to tell you what's wrong, but normally they aren't as tech savvy as you need them to be. They're, certainly highly motivated to help you, but they're often unreliable witnesses, and a lot of what they observe end up just being red herrings for you. And I'm sure you've been thinking this whole talk, like, why don't you just roll back to an earlier known good version when this happens? But the problem is that they need this feature right now. It's a new feature. They've bought this whole product on the basis of having this feature, and it's not working. So you're going to get into situations where you just need to fix it. You can't roll back. So let's now get stuck into how to embed diagnostics into your Python application. There's many fancy ways, but I'm going to show you what works for me. I use a pretty simple UDP setup. So the way it works is you connect your production app over UDP via a client to ask it, and you ask it to send you diagnostic information. So there's no fancy web front end, no structured data. All it is a UDP client run from the command line that sends a number, a page number, if you will, to that production app, and all that gets returned is a bunch of text. That's all. So there's no nested pages, no hyperlinks, no charts, no ability to send anything but a number and get nicely formatted text back. The advantage of this is really simple. It's easy to lock down or open up if you need to, UDP, or you can turn it into a fancy UI if you need to later on. The fundamentals are there. I'm not going to go through this whole thing, but this is the client side. So that's it in entirety. It's basically 40 lines of code lifted pretty much from the Python docs with a bit of exception handling. There's a section there up the top. You retrieve a number from the user somehow. I'm just using input. You send it across over UDP, and then you wait for the response, in this case block, with no timeout. Again, really simple. And then just print out the message you get back. And on the Python application side, so your handler, again, all it is a UDP server listening on a known diagnostic port. Again, straight out of the Python docs. It reads that page number requested by the client and has sub-handlers to process each specific page number request. You could use async IO, you could put it in a separate thread, make it blocking and use this built-in socket server module, which I have here. In many cases, the handling part happens so rarely that it's just fetching pre-computed info that you can easily put it in the main thread of your app without impacting anything, providing the listening component of the UDP port is made to be non-blocking. So just as an aside, I use a Python package called Blessed, which I want to give a little bit of love to make the text output all pretty in my diagnostics. So it just provides a nice interface for adding in those really complicated ANSI color escape codes. And you can see in the bottom picture, I'm basically printing it out from the terminal, and it works exactly the same as if you're printing it out in Python. It's all color formatted. Okay, so the first thing you're going to want to do with diagnostics is have a table of contents page at a known location. So in this case, 255 You remember that promise with REST, you know, the APIs would be self-revealing, self-documenting. You started at initial endpoint and discover all the rest. Well, that never happened, but table of contents has been around for ages. It achieves the same thing. And yeah, you can easily use a human-to-human interface where you just shout, I want Diagnostic 230 to someone on a phone in the field, and they go and get it, copy it, and paste it into a chat message or an email for you. So yeah, the subtitle of my talk was, you know, doing it without logging, but I've got an asterisk there, so it's not technically lying. But it's still really nice to have high-res debug logging to see if your app is ticking along. But with Diagnostics, it's good just to have a snapshot. Like last 109 lines or so is all you need. Every time you hit that page 245, it just gets the last 100 lines. And to achieve that, you can create your own circular buffer logger handler if you're using standard Python, or create your own logging classes if you're using something like MicroPython. And all that would do is output to standard output, but also at the same time storing in memory in a list that you can unroll when time comes to view that diagnostic. But the quickest win you can have with Diagnostics is reporting on unhandled exceptions and crashes. And you know, even if you are trapping it and you know, you don't care if it happens, you still want to know about it because you might want to make a specific error handling for it. So normally you want to write that to a file so it persists across reboots, and to carefully limit that file in size via rotation or similar to prevent running out of disk space. Now, I use a decorator. So the left is the implementation. It's one of those fancy ones that's an actual class that takes arguments. So the way you use it is you just, whatever function you're using, you just decorate it saying you want to consume the unhandled error, and it will still report on that unhandled error to your diagnostics. With getting crash data, that's also really, really useful. You've got a few options, not so elegant. You can take a look at sys.accept hook in the Python docs. You basically just register a function to use to run when any exception is hit, including unhandled ones. I don't really use it too much myself. You can trap signals, but you've got to be really careful with signals with not doing too much. And third option is the one I tend to use, is making sure every function call is within some sort of try except exception clause. So it's catching all the unhandled exceptions as well, and probably re-raising them. So in my crash file, I'll go and dump the entire contents of that circular buffer to provide at least 100 lines of context leading up to that crash. And then, yeah, using these little tricks to get it into that file before your application exits. So another really good use for diagnostics is if you've got some complicated state or calculations, you can put it in an easy to digest format, including the results of all the intermediate computations that went into generating the output. So it's kind of like a spreadsheet, you know, that shows all the steps in a really visual and intuitive way. So this kind of information would never be available in a black box, you know, product to the user, and it really allows you to potentially track down some pretty nasty edge cases while they're happening, the crime scene. Here you can see I'm showing on the left the evolution of each variable that went into a calculation and how it was adjusted before it got used. So that's very valuable to see. Why does it have that value? I don't understand. And yeah, as part of any troubleshooting exercise, particularly in the field, your technicians are going to want to know if the sensors are working, if there's communications back to base, etc. I'm showing some really simple diagnostic page handlers. This one here, you can print out the contents of a config file that users wouldn't ordinarily see, but still very useful to see what's happening. It's useful to know what's on disk, even how much space is left, even though I didn't show that there. And you can run systemctl if you're using systemd controversial. To view app status as well. And yeah, again, you're condensing down that information just to the bare minimum you need to provide that value during fault finding. More app metadata, knowing when your application has started and stopped and why. It may not be possible to work out, when it stopped due to a reboot, but I've put it there. And yeah, on the right-hand side, you do want to know all that nice stuff about the commit ID and the build number, so you can check out the right version of code to see if you can find the issue by inspecting your code, and if you want to branch off from that with a hotfix. Finally, I'll admit it's a bit of an abuse of the page number system to get it to actually do stuff, but you may want to consider providing common quick fix operations to users and to field technicians directly through this diagnostic interface. So stuff like rebooting, restarting services, clearing out files, that sort of thing. And yeah, when you do implement a reboot, the device diagnostic, you want to report that you're going to reboot, wait a little bit. There, that's the MicroPython example. And so they get the message and then reboot afterwards. Otherwise, it's just going to hang. Yeah, so that's about all I had to speak about. As I hope you can appreciate, I mean, embedded diagnostics, they're really powerful and they're, worth checking out. So give it a try.
Thank you, Jeremy. We have time for a question or two. So signal Jack, who can see past the lights, and make him run.
Yeah, so I had a question about, and maybe this is like a detail or something, but I wanted to know more about the page number system and if there's an advantage to doing it with page numbers as opposed to just like topic numbers.
Yeah, you could use, words or mnemonics to describe what you want. I've taken this approach from what's used in industrial field devices. They tend to use this type of system, and if it ain't broke, don't fix it. But there is also text-based lookups as well. Yeah, you could. There's no issue. Yep.
We've got one more.
Hello. I got really excited when you brought up the PDB debugger and you said, wouldn't it be nice if we could have that all the
which
time?
One?
Sorry?
What were you talking about?
Oh, the Python debugger, and you said, wouldn't it be nice if we could have the Python debugger all the time?
Yeah.
And I thought, I would love that too. And it reminds me of attaching a remote REPL in Clojure, and I saw your Python REPL there as well.
Yeah.
Do you know of a way we can just do that? Can we get a remote REPL in Python? Have you seen something like that we could do? And then we could find anything, whether we'd instrumented it or not?
Apart from just running GDB in production, I don't really know of a way. Yeah, it's a tough one.
No, thank you. I
There's
feel
a
like
performance hit as well, obviously.
I should have instrumented the commit hash, but I forgot. If only I'd remembered to instrument the commit
Yeah,
hash.
there's something. What you can do is run GDP over a network connection. So I've seen that being done
Okay.
as well, which is quite interesting. So
Cool.
take a look at that. It's a bit more lightweight.
I know a way. This isn't a question.
Okay.
Is
Yeah,
that,
go for it.
the Twisted framework has a module called Twisted Manhole, which
Okay.
is, I think it lets you telnet into your process, or SSH, or actually like SSH into your process, and from there get a REPL and do whatever you want. I remember a presentation given by someone at the very first Kiwi PyCon in 2009 on the subject. So I'm not too sure how up to date that is, but yes, there's a simple library that you can add to your process, which will just let you SSH into your process and then do whatever you want.
Yep. Yeah.
Not sure I recommend it.
Yeah. I don't know if you want to be modifying variables of a production application that's controlling a really expensive machine while it's running. Yeah.
Well, thank you, everyone. Sorry, hallway track.
Hallway track. Yep.
Thank you, Jeremy. Please enjoy your PyCon mug.
Thank you very much.
Thank you.